Hey! Hope everyone's doing okay. We're jumping into O-level physics, lesson 7, electromagnetic induction and transformers. Electromagnetic induction occurs when magnetic flux linkage through a conductor changes, producing an induced EMF. Move a wire across a magnetic field, move a magnet relative to a coil, or vary current in a nearby coil. If the circuit is complete, induced EMF drives current. A stationary magnet inside a stationary coil gives no continuous EMF because flux linkage is not changing. Induced EMF increases when flux changes faster. Move the magnet faster, use a stronger magnet, increase coil turns, or increase effective coil area. Reversing relative motion reverses current. Lenz's law states that induced current creates an effect opposing the change that caused it, consistent with energy conservation. Pushing a magnet into a conducting coil therefore meets a magnetic resistance. An AC generator rotates a coil in a magnetic field, continuously changing flux linkage. Slip rings and brushes connect the rotating coil to the external circuit, producing alternating EMF. Faster rotation or a stronger field increases peak EMF. A simple DC generator can use a split-ring commutator to make the external current unidirectional, unlike the slip rings of an AC generator. A transformer uses mutual induction between primary and secondary coils wound on a soft iron core. Alternating primary current makes changing core flux, inducing alternating secondary EMF. A steady DC input does not produce continuous secondary voltage. For an ideal transformer Vp, all over Vs equals Np, all over Ns. More secondary than primary turns gives a step-up transformer, fewer give step-down. An ideal transformer conserves power, VpIp equals Vs's. If 240V is stepped down to 12V and secondary current is 4.0 A, output power is 48W. So ideal primary current is 48, all over 240 equals 0.20 A. Real transformers lose energy through coil heating, eddy currents, and imperfect flux linkage, so output power is less than input. Power transmission uses high voltage to reduce current for a given power. Cable loss is P loss equals I squared R, so lowering current sharply reduces heating. A step-up transformer raises generator voltage for transmission, and step-down transformers provide safer consumer voltages. High voltage does not itself reduce required transmitted power, it allows the same power at smaller current and therefore smaller resistive loss. State exactly what flux change occurs and how its rate changes. For transformers, use the turns ratio first, then power balance or efficiency, keeping primary and secondary quantities clearly labeled. A transformer has 500 primary turns and 50 secondary turns with 230 V input. Vs equals 230 x 50, all over 500 equals 23 V. If output is 46 W, ideally, secondary current is 2.0 A. Do not claim a stationary magnet continuously induces current. Use DC for normal transformer action, reverse the turns ratio, or say high transmission voltage increases cable current. Practice. A transformer has Np equals 800, Ns equals 200 and Vp equals 240 V. Find versus. Answer: Vs equals 240 x 200, all over 800 equals 60 V. Watch the numbers land in the matching symbols. Check that units cancel cleanly. If they do not, the setup is wrong even before the arithmetic. Practice. A 95% efficient transformer takes 500 W. Find output power and explain why high transmission voltage reduces loss. Answer: output equals 475 W. For fixed power, higher V means lower I, and I squared R loss falls. Watch the numbers land in the matching symbols. Check that units cancel cleanly. If they do not, the setup is wrong even before the arithmetic. Okay, That's it for electromagnetic induction and transformers today. Next time in O-level physics, we'll get into atomic structure and radioactivity. Stay curious and see you in the next lesson.